Okay, here's a work energy problem. I just partially made this up, but I made up the numbers to protect everybody. Okay, so here is the Earth, and here is a spacecraft that's traveling near the Earth. And so it starts here at a position R1 with a velocity V1, and then it moves further away up to here R2 with the velocity V2. And we want to find out what the velocity of V2 is if I know the velocity at R1 and V1. So it's mass of the Earth. I know the radius. I picked the radius of 1. This is about a third of the way to the moon, and then that's about at the moon. So it's a spaceship. I don't know. Spaceship. Okay. Oh, and then we need G. We're going to need this too. G equals 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. Okay. You might say, hey, I like the momentum principle. Let's use the momentum principle. But you can't do that. Okay. You can't do that because, look, right here, the gravitational force is right there. Right here, it's like there. Okay. So not only does the gravitational force change in direction, but it also changes in magnitude. On top of that, we don't know how long it takes to get from here to there. So it's a really, really difficult problem to do numerically. No, I'm sorry, not numerically, but with momentum principle. You could do it numerically, and that wouldn't be too bad. Okay. In fact, maybe I'll do that in class or something. I don't know. It's a good problem. Okay. So there's that. So momentum principle doesn't work. So we need to use the work energy principle. Now, a lot of people say, okay, work energy, I know that. Work equals change in energy equals the change in kinetic energy. And work equals F dot delta R. That's not going to work. That's not going to work because, again, look at this. Delta R, delta R, delta R. Delta R changes in direction. The force changes in direction. The force changes in magnitude. If you want to do this, you'd actually have to integrate the force along that path. And that's not super easy. There are some tricks you could do that make it pretty easy. But overall, it's not easy. So don't do that either. And don't just calculate one force and then use that for the change in R or something. That's really not good either. Okay, so what are we going to do? We're going to use the work energy principle. We have to, because we're dealing with a change in displacement. But the first thing to do is say, what is the system? And it's going to be the Earth plus the spacecraft. If I take the system of both the Earth and the spacecraft, then ignoring the sun and all that other stuff, which I could safely do in this case. In that case, there's no work done on the system because the only forces are internal forces, this internal gravitational force. But that means that since I have both the Earth and the spacecraft, I can have a gravitational potential energy. So in that case, I can say work is 0. And it's going to be equal to the change in kinetic energy plus the change in gravitational potential energy. So I can write that as 0 equals K2 minus K1 plus U2 minus U1. And I want to solve for the velocity at 2. So this is really the term I care about. So I can write this as K2 equals K1 minus U2 plus U1, where the potential energy, well, I'll write it in just a second. I'll write it right now. Okay, so let's put in values, expressions for the kinetic energy and the potential energy. So this is going to be 1/2 m of the spacecraft, V2 squared, is 1/2 m of the spacecraft, V1 squared, minus the potential energy at 2, which is going to be negative G m1 m2 over R. So it becomes positive because there's 2 negatives. G m mass of the Earth over R2, and then I have plus another one, but this one's negative, G me over R1. So all I did was pick my system, set that equal to the change in energy, and then essentially get to the one that I don't know, which is velocity 2. You'll notice here that the masses cancel. The mass of the spacecraft cancels. So I can multiply by 2, and I get V2 squared equals V1 squared plus 2 G ME over R2 minus 2G ME over R1. I feel like that's backwards. Oh, yeah, that's good. That's good. Okay. So now I can just take the square root of both sides. And then that's it. Okay, so just so you can check your numbers and stuff, here I picked the mass of the Earth, 5.97 times 10 to the 24th kilograms. R1 is 1 times 10 to the 8th. R3 is 3 times 10 to the 8th. And V1, actually, the first number I picked was wrong. I'll tell you why. V1 was 3,000. When I do that, I get V2 equals, and you can check me on this one, 1921 meters per second. And so the important thing is this is slower than that. As it moves further away, it's going to be slowing down because gravity is essentially pulling backwards on it most of the time. The first time I picked a value and I had an imaginary number inside of here, I mean a negative number, because if you pick this value too low, it won't get that far. It'll get over there and then come back. So you can't just pick whatever numbers you want. And that's what I did the first time. I picked it and it didn't work and I made a mistake. But this is good. It's lower than that, and it's not an imaginary number.